Good evening and welcome to review of AB Calculus, Limits and Derivatives. Okay, so far, up until this point, we have learned how to find limits and we have learned how to find derivatives. And you need to be able to know how to find limits graphically, numerically, and analytically. What do I mean by graphically? Well, you should be able to recognize when a limit exists or it does not exist graphically. And I've shown you guys that before. I've said it does not exist when you have a break, when you have an asymptote, and when you have oscillating behavior. Okay, numerically, when do I want to use a numerical way of finding a limit? So numerically, that means I use a table of values, and I want to use this method when I can't use direct substitution. So this is something that I want to do. This is one of my strategies. And then you must also know how to find derivatives analytically. That's just the same as algebraic. So can you factor? You need to be able to recognize when you can factor an expression so that you can use direct substitution. Another method is rationalizing your numerator. And then, and just using other algebraic techniques to be able to manipulate your expression and make it easier to work with. Okay, and you've also learned about derivatives. And with derivatives comes the idea of continuity. Okay, so if you can find your derivative, if your function is differentiable, then that means that you do have a continuous function. However, the opposite is not always true because, again, you can have a function that is continuous, but you cannot find the derivative at a certain point, like what's it called, a absolute value. Okay, this is a continuous function, yet you cannot find the derivative at that sharp turn. So that goes hand in hand with a graphical approach to being able to find your derivative. Okay, so you should be able to do that graphically. Like if I give you a graph, you look at the slopes of your graph, and that will determine where your derivative graph will be. You should be able to do it numerically. This is like when you plug in a number after you find the derivative, and then you should be able to do it analytically. So this is like your power rule, your quotient rule, the low d high minus high d low all over low squared, and this is also your product rule. So all these rules that you've learned so far, these are ways of finding your derivative analytically. And in addition to be able to do all of these things graphically, numerically, and analytically, you must also be able to do it verbally. So that's like those problems, like on your homework. And verbally sometimes can mean understanding something like this, like on your homework page 105, number 53 and 54. Where we have different situations and they give me descriptions of what I need to be able to interpret. For example, on number 53, f of 0 equals 2. Well, I have to know that that's just a point. Okay, and then for these ones you were supposed to identify a function f that has the following characteristics. Okay, so you need to be able to interpret these things, these statements. So this is just a point. So I have a 0.02. And remember, your derivative is just your slope. So I have a negative slope. Look at that negative. I have a negative slope everywhere. That means everywhere. From negative infinity to positive infinity. So slope of -3 everywhere. So 1, I need to go down 3, 1, 2, 3 over 1. Down 3, 1, 2, 3 over 1. So I have a function that looks like this. It has a point, it crosses through 0, 2, and it has a slope of -3. That doesn't mean I'm graphing -3. That means I'm graphing the function that has a slope of -3. Okay, for 54, again, the first statement, f of 0 equals 4, that's just a point again. That's my first hint of identifying a function that has those characteristics. So that's just a point. So at 0, I go up 4. That's my first point. Then I have that f prime of 0 equals 0. So what does this mean? That means I have either a minimum or maximum at 0, because remember I said that only at a min or a max you will always have a slope of 0. So if I have a min, I have a slope of 0. If I have a max, I have a slope of 0. So that's what I'm going to draw right here, because I'm not sure which direction it goes yet. I either have a min or I have a max. Okay, and this is telling me that I have a negative slope for all of my units from my domain where x is less than 0. So where x is less than 0, so here's 0. When x is less than 0, it's that direction. So that means I have a negative slope. Which of these two has a negative slope? If you said the top one, you're right. So this piece right here has a negative slope. Okay? Then I look at my other clue, my last clue right here. F prime of 0, f prime of x is greater than 0 for x is greater than 0. So again, here's 0. So in this direction, it's telling me that I have a positive slope. And again, I'm looking at these two. So which of these little parts of my graph have a positive slope? If you said the top one, you are right again. So my function f would have looked something like this, where I have a slope of 0 at 0. I have a point at 0, 4. I have a negative slope for all of my x's less than 0. And I have a positive slope for all my x's greater than 0. That would be my answer. And one of the important things that I wanted you to get out of the limits is using the one-sided limits, especially to solve these kinds of problems that I have up here, where you have to find or any constant such that the function is continuous. So remember, in order to do these, you must set up your left-handed and right-handed limits. So for the left hand, the left side, okay, which of these two domains tell me the number is less than 0? The first equation will. So if I set up my limit of as x approaches 0 from the left, I'm going to use this equation right here, 4 times sine of x over x. And then for me to find the right-handed limit, I'm going to set up another limit expression, the limit of a minus 2x as x approaches 0 from the right, because these are all the numbers that are greater than or equal to 0. So, and I'm going to evaluate it. So this is the limit of x x approaches 0 from the left of 4 times sine x over x, and if you remember, this is a special trig limit that equals 1. So this whole limit right here equals 4. Okay, and then I have to solve my right side limit. So I'm just going to plug in 0 because there's nothing for me to simplify here. So just direct substitution now. So the limit, I don't need limit anymore. Just kidding. So if I just use direct substitution, I get a minus 2 times 0, which is just 0. That's 0. So I just get a. And then after I'm done evaluating both my left and my right limits, then the last step that I have to do is equate the two answers that I get. So set them equal to each other. A equals 4, and that is my answer. So this function would need to be equal to, or the constant would need to be equal to 4, so that my function makes a continuous line. Because remember I told you that sometimes it can break. So you need to force it to be the same dot, the same point, so that they can be a continuous function. We don't want to break. We want it to be continuous. We want the left side to be equal to the right side. And back to our intermediate value theorem. So basically, all this is saying is that if I have, so let's say I have a, let's see, A, B. If I have an interval AB, and there's a number in between, or and then if I can evaluate that, so let's say I have a function, and I plug in f of A and I get a number, and I plug in f of B and I get a number, and then say I get like 2 and 25. So what the intermediate value theorem tells me is that if any number in between 2 and 25, say like 5 or maybe even 10 or 23, any of these numbers, there must be a number in between the interval A and B such that when I plug that number into my function, I get 5, 10, 23, or whatever else in between. And another top thing that you need to know is the definition of continuity. Okay, so I showed you where your limit can fail to exist, and then now we have a definition of continuity. So in order for a function to be continuous, it must have a limit. So the limit exists. It also must say, like, the limit of my function as x approaches a number must be equal to that point. Okay, so in English it says the limit equals where the function is defined. It's the function is defined. So sometimes when you have like that function that has a hole that's redefined somewhere else, well, this is not continuous. Why? Because the limit does not equal whatever that point is. Okay, so say like this point was 5. What is the limit of f of x as x approaches 5? Well, it'll be where that line is. So trace a line, say this is like 2 or something, so it equals 2. But where does f of 5 equal? Where's that? It's at this point up here, which is probably like 3. So f of 5 equals 3. So in this case, they're not equal to each other, so this function is not continuous. And the last requirement for continuity, so we have first, the limit must exist. Second, the limit equals where the function is defined. And lastly, it must be continuous. So it must be, there shouldn't be any breaks, there shouldn't be any asymptotes. And this definition of continuity, all these 3 things must happen in order for you to be able to find a derivative. So they're all related back to derivatives. Okay, and other than that, like if you know the rules for the derivatives, you should be okay on the quiz tomorrow. Okay? Good luck. Bye-bye.